Alrighty, folks. So, this is going to be our week 3 problem session. And I'm going to have to change my pen real quick. Let's get a fine point pen. I'm going to check real quick. Yep, okay. Still going. So, we had a number from the homework, a number of repeat ones from the homework, so definitely going to hit those. So the first one we're going to do is going to be the homework problem, or a homework problem, like number 7. And I'm actually going to do 2 of these because there's 2 different possibilities that might show up, right? And the question was something like, is f continuous? And f itself was a piecewise function, so f of x equals 3x plus 1 for x less than 4, and for negative 2x plus 2 for x greater than or equal to 4, right? Now, we remember that when we're trying to find continuous for piecewise functions, there's 3 things to check, or rather 2 things to check. 1, are the pieces continuous? And 2, is it continuous at the change points? Right? Remember, the change points are the numbers in the domain where it switches from being in one piece to another piece. With 1, we're definitely set, right? Because this piece right here is a polynomial, and we know polynomials are continuous. And this piece right here is also a polynomial, and we still know that polynomials are continuous. So the pieces are continuous, and all we have to do is make sure it's continuous at the change points. So, the definition of continuous at a point, right? In this case, our change point is 4. And we only have 1 because we only have 2 pieces to change between. So there's only 1 moment where it changes. So continuous at 4 means that f of 4 equals the limit as x goes to 4 of f of x. So there's some things hidden in here. 1, f of 4 has to exist as a number. Right? 2, the limit as x goes to 4 of f of x has to exist as a number. Right? So in other words, it can't go off to infinity. And 3, those 2 numbers must be equal. Right? So, to work on part 1, right, f of 4, we have to consider what that is. Now, when we're looking at function values of a piecewise function, that means we need to take our input, which is 4 in this case, and figure out which of these 2 statements are true when x equals 4. So if x is equal to 4, then is x less than 4? No, because 4 is not less than itself. I already have x's being used. Is x greater than or equal to 4? Yes. 4 is in fact equal to 4. So if x is 4, then x is greater than or equal to 4. Right? So that means that we plug it into our function. So f of 4, we plug into the piece that said yes, and we get negative 2 times 4 plus 2 equals negative 6. Right? So, first piece done. Second piece, the limit existing, that also has 2 sort of aspects to it, right? For that to be true, we need the limit as x approaches 4 on the left of f of x to equal the limit as x approaches 4 on the right of f of x, right? That's what it means for the limit to exist, is that the limit on both sides exists and it's equal to each other, right? So the limit as x goes to 4 on the left of f of x, right? Going to 4 on the left, remember, means that we are getting close to 4, but we're always less than 4, right? Things on the left on the number line is less than. So if we're always going to be less than 4, right, we're living in this piece. So this is going to be the same thing as x approaching 4 on the left for 3x plus 1. That's a continuous function we know now, right? For f of x we don't know, but we do know for that polynomial. So that's going to be 3 times 4 plus 1, or 13. Right? The limit as x approaches 4 on the right of f of x. Remember, that means that x is getting really close to 4, but it's always bigger than 4. So that means that this statement here is true. So we're in this piece again. Limit as x goes to 4 from the right. And again, that's a polynomial. It's continuous, so we can just plug in, and we get -6. So these two limits are not equal, so this does, but this doesn't. And so it's not continuous. And specifically, this problem asks you to not only say whether it's continuous or not, but to figure out why it's not continuous, right? And so it's not continuous because the limit as x goes to 4 of f of x does not exist, right? So you might have gotten a different version of that problem where maybe you had an f of x that looks like right? So this, we got the same thing. The two pieces are continuous. Because the two pieces are polynomials. And at the change point, that's going to be x equals 1. So we need to know, does f of 1 exist? Right, so we look at 1, we say, okay, for x equals 1, is the statement x is less than 1 true? Well, no. If x is equal to 1, then x can't be less than 1. Right? And then we look at the other statement, is x greater than 1 true? No. If x is greater than 1, then x can't be equal to 1. So f of 1 does not exist. And if f of 1 does not exist, it can't be equal to anything. So f of 1 is not equal to the limit as x approaches 1 of f of x, right? It may be, and it actually winds out, that this, the limit part, is actually equal to 5, right? If we went through the same work we did up there, we'd get the same thing on both sides, and we'd figure out that the limit is 5. But f of 1 does not exist. We are not allowed to plug 1 into this function because neither of the pieces are true, right? Neither of these pieces are true when x equals 1. So f of 1 does not exist, and this function is not continuous because f of 1 does not exist. All right? Okay, so the next problem that people asked about was number 8, and it was very similar. So it had a function that looked like this. And it wanted you to find C so that f of a is continuous. Right? So again, we look at this, and here C is just a number. It's a constant. It's not a variable. It's one particular number. We don't know what it is yet, but it's a specific number. A here is our variable, right? It's what shows up on the right here, and it's what shows up inside the function. So 1, we got to look, are the pieces continuous? And this is going to be yes for any C. Right? Because if A is the variable, these are just polynomials, right? They're single variable polynomials. And as we talked about in these sections, polynomials are always continuous, right? So 2, we need to look at the change point. And that's going to be when A equals 4. Right? It's when it changes over from being on one piece than the other. So we need to know, does f of 4 equal the limit as x goes to 4 of f of x? Sorry, those x's should be a's. Right? So we need that to be true. Right, and so let's first figure out, does f of 4 exist? Right, so that's looking when a is equal to 4. Is a less than or equal to 4? Then, yeah, that's true. Right, is a greater than 4? No, that's not true. Right, so this is the piece we need to be looking in. We know that it exists at this point. And specifically, we know that to get what it's equal to, we need to look at the piece associated with that statement. So that's going to be this piece. It's going to be C times 4 plus 7. Right? So we don't know what that number is because we don't know what C is yet, but that's what f of 4 is. Right? C is a number, so we're good there. Right? Now we want to figure out whether the limit as a goes to 4 of f of a exists. Right? And it better be true, so if we get to a point where we need to figure out if something's true, well, we'll see what we get there. Right? So that means we want the limit as a goes to 4 from the left of f of a to equal the limit as a goes to 4 from the right of f of a. Now the limit as a goes to 4 from the left, remember that's going to be a getting really close to 4 but always less than it. So if we're close to 4 but less than, we're going to be in this piece. That piece is just continuous. So this is again C times 4 plus 7. So one of the things, the fact that these two guys are the same, we can conclude we don't even have to check step 3. If these two one-sided limits are the same, it's automatically going to be equal to whatever f of 4 is. Right? So that's a good sign. Right? Whereas over here, the limit as a goes to 4 from the right of f of a, if we're at the right of f of a, we're always bigger than, or if we're at the right of 4, we're always bigger than 4. So we're looking at this piece down here. So we get that this is ca squared minus 7. That's just a polynomial, so we can plug in. Right. So now we have two linear functions of c, and we want them to be equal. If they're not equal, then we're not continuous, and we want it to be continuous, right? This problem isn't figuring out if it's continuous. This is making sure that it is, right? So what does C need to be so that this is true, well, I'm gonna, let's see, add 7 to both sides and write this a little bit more normally. I'm going to subtract 4c from both sides. And I'm going to get c equals 12, or 14 divided by 12. Right? And that means that if c is 14 divided by 12, these two right-handed limits are equal, for c equals to 14 over 12. And since this limit and this limit were the same, that means that, so what we really wanted, let me write this out, was f of 4 to equal the limit as a goes to 4 of f of a. That's going to be c4 plus 7 equals c4 plus 7 equals c16 minus 7, right? Because those are two different ways to write down the same limit. And this is true for c equals 14 over 12. Right? So generally for these types of problems, it's always going to come down to finding the one-sided limits and setting them equal to one another and solving for c. Right? Because this value, as long as it exists, right, you still have to figure out that it exists. But once you know it exists, it's always going to be equal to one of the two one-sided limits. Right? This wasn't just a coincidence or a nice function that I found. This value, if it exists, is always going to be equal to one of the one-sided limits. Right? So if you figure out where the one-sided limits are equal, that's going to get you the whole kit and caboodle. You don't actually have to check step 3 like we kind of did here. This was extraneous. Right? Once we got to this point, we knew what we had. Right? So, next problem asked about was number 11. And that was one that looked like that goes to 12. Something along these lines, right? And so if we did substitution, right, which is always a good first shot, we'd get 1 over 12 minus 1 over 12 over 12 minus 12, which is 0 over 0, right? So we know we're in an indeterminate form, and that means that we need to do something so that we can factor and cancel, right? So it's a little hard to factor things that look like the stuff up top. So my first thing to do would be to simplify fractions, right? In fact, whenever I have a complex fraction like this, I always want to simplify it, right? And one of the ways to think about simplifying is you want to multiply through everything by all of the small denominators, right? So I'm going to take this that we have here and multiply through by 12, because that's a small denominator, and y, because that's a small denominator. And I'm going to do that on the top and bottom so that I'm not actually changing anything. All right, so the bottom, I'm going to leave because we're going to want to factor it anyway, so there's no need to multiply through and then factor again. All right? But when I multiply 12y by 1 over y, I just get 12. And when I multiply it by 1 over 12, I just get y. And I notice that these two pieces, this one here and this one here, are the same, but their subtraction is reversed. So that means I can cancel them, but I get a -1 instead of just a 1. All right. Now I do substitution again and get -1 over 12 times 12 -1 over 144. And that means that we were good here, and this is our final answer for that guy. All right. So, next one on the homework. There's another one that we'll talk about briefly. We won't actually work out. That's a lot like this one, except instead of specifically having 12 here, it just has the letter A, right? And in that case, A is standing in for a constant, and we do the exact same work. It's just everywhere we wrote down a 12, we write down an A instead. But I'll mention it again when we get to that problem. All right. So that was asking for a limit like this one. All right. And so if we do substitution, again, we get the square root of 9 minus 3 all over 4 times 0, which is 0 over 0. So it's an indeterminate form, and it's the type that we probably want to do factor and cancel with. Right? But again, we've got something weird to factor here, so we're going to have to simplify it. And the way we do this type, because there's a square root involved, is instead of multiplying by the small denominators like we did up here, we're going to multiply by the conjugate. So, the conjugate means take the square root piece and leave it the same, take the non-square root piece and leave it the same, and take the thing in between it and change it, right? So it started off as a subtraction, we're going to change it to a plus. If that had started off as a plus, we change it to a subtraction, right? Whichever way we need to change it, we just want to have the opposite. And that's the thing. Remember, we take the whole, we don't change the thing underneath the square root. We want the two square roots to look exactly the same. Otherwise, this trick with the conjugate doesn't work because it's not the conjugate anymore. Right? And the reason why we multiply by the conjugate, this stuff down here just sticks around, so we get that. And the reason why we multiply by the conjugate is whenever you do that, you take the first two things and you square it. And the reason why we do this for square roots is because squaring square roots just makes them go away, and we get 3x plus 9. Right? And then we take the other piece that's exactly the same and we square it, and we always have a subtraction there, right? Regardless of whether we have a plus or a minus here, if we're multiplying by the conjugate, it's always the square of the first minus the square of the second, right? And that's nice for us here because these cancel out, and we get the limit as x goes to 0 of 3x over 4x times this stuff, right? And here comes the point where we can cancel, right? The general rule for this is factor and cancel, where factor is sometimes more complicated than just factoring, right? But we have an x on the top and we have an x on the bottom, so we can cancel both of those. And we get 3. Right, so we get that guy. Now we can try substitution. Right, and that gets us 3 up top, so it's definitely not going to be an indeterminate form. And we get the square root of 9 plus 3. So that's going to be 3 over 4 times 6, which is 1 over 8. And since that's just a plain number, then our substitution worked, and that's going to be our final answer there. Right? So moving on to problems from the book. The first problem actually leads from that very nicely. So in section 2.5, number 24, looks like the limit as x goes to 4 of the square root of 5 minus x minus 1 over 2 minus the square root of x. Right? So if we do substitution, right, we get the square root of 1 minus 1 all over 2 minus the square root of 4. And that is 0 over 0. So it's an indeterminate form. And it's the type where we want to factor and cancel. But in this case, it's not just one of the pieces that's hard to cancel. It's both of them, right? They both have a square root in them. So the trick for dealing with those is do the same thing we did last problem twice, right? So we're going to take this guy. And we're going to multiply top and bottom by the conjugate of the top. So that's taking that first piece, leaving it exactly the same, but changing the sign that's outside. Right? We got to do that top and bottom so we don't change anything. Then we're going to also multiply by the conjugate of the bottom. Right? So we're going to take the first piece and then change that subtraction to a plus and have the second piece here. Right? We're going to do that top and bottom so that nothing changes. Right? So when we multiply these two together, they're conjugates of one another. So we get to use our conjugate rule. So that's going to be the first piece squared minus the square of the second piece. All right. And we're just going to leave this other bit here because, again, we're eventually going to want to factor this. There's no need to multiply it through and then have to unfactor it. All right. And down here, we're going to multiply these conjugates together. Right. So that's going to get the first bit squared minus the square of the square root, just gets us x. And we're going to leave this here. Right. So this becomes the limit as x goes to 4 of 4 minus x up top. Oops. And it's going to become 4 minus x down here below. Okay. And there we factored it, so now we can cancel. So this is the limit as x goes to 4 of 2 plus the square root of x all over square root of 5 minus x plus 1. All right, so now we can try substituting again. And we get 2 plus the square root of 4 all over the square root of 1 plus 1. So that's 4 over 2 or 2. Right? So we use the same trick. If it's got two things that we need to take the conjugate of to factor them, well, then we just take the conjugate of both of them. Right? And one thing to notice is that we always leave, if we didn't write something down specifically to simplify the, in this case, the top, right? We didn't write this down to simplify the top. We wrote it down because we had to in order to simplify the bottom. And anytime we've got something like that, we just leave it, right? And worry about the rest of it. The whole point of this process was to simplify this piece, right? So we work on simplifying that piece. And the whole point of the process was to simplify this piece. We work on simplifying that piece, and we leave the extraneous stuff be, right? Because the other nice thing about the conjugate in this situation is if the original went to 0, the conjugate's not going to go to 0, right? That's just a rule. That's just how it's going to work. So we can just leave it there, and it's not going to send us back into an indeterminate form. Right? Same as we did down here, right? It looks less complicated because it doesn't have a square root down here. But this piece was just to simplify this piece. So when we have it here, we're not going to mess with it. It's going to stick around. It has to be there so that we didn't change anything. But we're just going to let it follow us till the end and trust that it's probably not going to make any trouble for us. Oh boy. Let's see. I think I can do one more problem in this space. So 2.5, number 38. Right? So this one said use the identity a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. Right, so that's a formula that's hopefully familiar from pre-calculus. It's a factoring formula. And when we have something like this, right, it can come in handy. Because if we do substitution, we get 3 cubed minus 27 all over 3 squared minus 9, which is 0 over 0, which, among other things, tells us that this is x cubed minus 3 cubed, right? Otherwise, when we subtracted them, we wouldn't get 0. And x squared minus 3 squared. It didn't remind you about the difference of squares formula. I guess they're assuming that one stuck in a little better in the brain. But we can factor both of these. The top one becomes x minus 3, because in this case, x is a and 3 is b. So the next one is x squared plus 3 times x plus 3 squared. And that's going to be all over, if we remember, difference of squares is just the difference of the two pieces and the sum of the two pieces, right? It's the reverse of the conjugate rule that we just used in those past two ones, right? These two are conjugates of one another, so when we multiply them together, we're going to get the first one squared minus the second one squared. So when we want to factor, we can do it that way. Oops. Got to keep our limit going. Right, and now that we factored it, we see we can cancel. Right, and we get limit x goes to 3 of x squared plus 3x plus 9 all over x plus 3. And now that we've canceled, we can try substitution again, and we get 3 squared plus 3 times 3 plus 9 all over 3 plus 3. It's going to be 9 plus 9 plus 9, so 27 over 6, or 9 over 2. Right? And that's a solid number, not an indeterminate form, so that's going to be our final answer. Right? Alrighty. So, let's see. So let's go to another canvas. Check and make sure. Okay. Gotten a little bit paranoid because it keeps cutting out on recording on me, and I didn't want all of that to be wasted. So, next one was from 2.5 again, number 49. And this one and the next one I'm going to talk about. I'm not actually going to do number 54. I'm just going to talk about it. But both of them said something along the lines of evaluate in terms of the constant A. All right. So, what that means is that A is a number that we don't know what it is, right? But any of our rules, like constant multiple rule or the limit of constants, any of those rules will work for A because A is just a number. It's not a variable. It's just a constant, right? So that's what this tells us. In terms of means that there's probably going to be an A in our final answer, and that's fine. Right? It means that they are expecting an answer that probably has some A's in it. right? It's not guaranteed to. If you get an answer without A's, that doesn't mean you did it wrong. But if you get one with A's, that is allowed. Right, so 49 has the limit as h goes to 0, right? That's another thing that tells us that A is a constant, because as far as limits are concerned, only the thing beneath them is variable. All over h, right? And if we plug this in, if we do substitution, we get 2 times a squared minus 2 times a squared over 0. And that's 0 over 0 no matter what a is. So we've got an indeterminate form. So we want to factor and cancel. There's no weird square roots or complex fractions here. So probably we just want to multiply some things out and see where that gets us. So we'll multiply out that parentheses, right? The sum of things squared is the first one squared plus 2 times the product of both of them plus the second one squared minus 2a squared over h. We can multiply that 2 through to get 2a squared plus 4ah plus 2h squared minus 2a squared all over h. And hey, there's some canceling. It's not canceling out the zeros yet, but it's canceling. Right, so we get the limit as h goes to 0 of 4ah plus 2h squared over h. Now this looks like something we can factor, and specifically factor to get rid of the denominator, right? Because we can pull an h out, get 4a plus 2h, so the h's cancel, and we get the limit as h goes to 0 of 4a plus 2h. And now when we do substitution, we get 4a plus 2 times 0, which is just 4a. And that's just a number, because a is just a constant. So our substitution was good, and our final answer is 4 times a. Right? So 54 I'm not going to do, right? I will write out what it is. This has the same instructions, and it looks like the limit as h goes to a of 1 over h minus 1 over a all over h minus a. And I just want to call our attention that this is exactly like problem, I think it was 11. Yeah, problem 11, except instead of a number that we know, we have this constant that we don't know, right? And instead of y, our variable is called h, but that's just a change in name. That doesn't change anything. If you really wanted to, you could rewrite this problem and replace all the h's with y's, right? So doing this problem is going to be exactly the same as working out number 11. We're going to want to cancel out those smaller fractions by multiplying with an h and an a, and then we're going to see what we can cancel and see what's left over for us, right? So I mostly just wanted to call the attention there that what number that was, right? The difference in problem 11 between all of your problems is what number a is in this case, right? I chose 12, yours might be 7 or 4 or 3, but it's all going to be exactly the same problem. It's going to be this problem where a different a is plugged in, right? And changing the name of the variable should never be a problem, right? If you ever don't like the variable they use, just pick a different one that's not already in the problem and change all instances of it. It doesn't actually change the problem. You'll just want to make sure to change it back if you have to plug it into the computer or something like that. Right? Okay. So that wraps up our questions from section 2.5. So from section 2.6, we had a question about number 47. And that one was a tricky one. And it's a good thing we have plenty of room on this canvas because we're going to go through a couple things that didn't work. Right, if we do substitution, first off, we get 1 minus 1 over 0, which is 0 over 0, and that's an indeterminate form. So we've got to, well, if we were in last section, we'd have to factor and cancel. In this section, we know that it's probably going to come down to using 1 minus cosine over theta. The limit as theta goes to 0 is, oh shoot, now I have to remember what it is. It's either 0 or 1. This one's 0. And the limit as theta goes to 0 of sine theta over theta equals 1. Right? So since it's in this section, we're probably going to boil down to figuring out how to use these two. Now the key problem that we have here is that we've got two different inputs. Right? I did a bunch of problems when in the mini lecture for this section where we could change what the input of cosine was by doing a variable substitution, right? Maybe we'd say x is equal to 2 theta, and then we'd make all the other changes that we need to make, and we'd wind up with something that looked like one of these two, right? But in this case, we can't change one of the variables in cosine without changing the other, so neither of them are we going to be able to write as both just the same variable at the same time, right? So what this makes me think of is the double angle formula, because that is a formula that we have for trig functions that let us change things that have 2 theta in them to just have theta in them, right? And we want all of our inputs to the trig functions to be the same to use our trigonometric limits. Right, so the double angle formula is cosine of 2 theta. It's actually a complicated one. It can be 3 different things. It can be cosine squared theta minus sine squared theta. It can be 2 cosine squared theta minus 1. Or it can be 1 minus 2 sine squared theta. So when I saw that this problem was on the list and I tried to work it, I actually plugged in all of these, right, to see what helps. So I'm not going to do the whole, like I'm not going to plug it in and write everything with it, but I am going to see what I can do here, right? So if I do the first one, then I get cosine squared theta minus sine squared theta minus cosine theta, right? So we can split this up a little bit, right? We could do minus sine squared theta over theta as its own fraction. And then we could add to that cosine squared theta minus cosine theta over theta, right? That's something you can do with fractions. This we can find the limit of, right? That is going to involve using this, the product rule for limits, and that bottom trigonometric limit. So that one's good. If the second one is good, then we'd be solid, right? So, right, so that's good. We can pull out a cosine here. I'm actually figuring out this may have been simpler than I had made it. Right. Okay, so nothing we can solve quite yet, but we can continue using algebra as our friend. Right, maybe we make this minus so that we can have a 1 minus cosine theta. Right, we want to make it look more like this. And then we can do some more algebra. Yeah, this is going to actually wind up a lot easier than I originally thought it would, because that's cosine and 1 minus cosine theta over theta. Right, so let me write this out completely explicitly. Right, so we've split it up. We've factored everything out. This we know how to take the limit of, right? Because that's a continuous function. This we know how to take the limit of because of our trig limits over here. This we know how to take the limit of because it's a continuous function. And this we know how to take the limit of because of our other trig limit up here, right? So now we can put this all together. Right, this is going to be equal to the limit as theta goes to 0 of negative sine theta times sine theta over theta minus cosine theta times 1 minus cosine theta over theta. Right, and we can use the product and sum rules because all of these limits exist. That's going to be what we get when we plug in 0 to sine. This we know is 1. That's going to be what we get when we plug in 0 to cosine. And this we know is 0. Right? So we get 0 out of this. And so if this one hadn't worked, right, if we hadn't seen how to make that simplification, then we can try all of the others, right? The first time I did this, I actually went through all 3 of them and couldn't make it work till I got to here. And it's slightly simpler looking if you use that one, but you get 0 out of it either way. But so using these trigonometric limits boils down to being comfortable using your identities to simplify it so that all of the inputs are the same, right? And then comfortable doing algebra on what's left over until you can break it apart into these individual factors that you know how to do something with, right? So the trickiest one to remember is that you can look for 1 minus cosine theta over theta probably. This just looks like regular factoring. But this is the only factor with cosine in it that'll work. Right? If we try to do something with cosine theta over theta, that goes to infinity. That doesn't help us. Right? But if we split it up this way, we know where all 4 of these pieces go. Right? So that was 47. Got one more problem from this section. So 2.6, number 55. So the instructions here said use, let me make sure I'm getting the exact instructions. Use the results of exercise 52, and that result is that the limit as h goes to 0 of 1 minus cosine h over h squared is equal to 1/2. Right? So that's what exercise 52 said. And for the purpose of these exercises, you don't have to know why that is. You don't have to have done exercise 52. It just says that you're allowed to use it. So exercise 55 itself is the limit as t goes to 0 of the square root of 1 minus cosine t all over t. So the thing to realize here is that this is going to be the same as 1 minus cosine t over t squared. Which we know that the square root is one of the nice functions, or rather the square root is the 1/2 power, so we can actually pull it out like that. And this, what we have right here, is exactly the same as what we talked about in exercise 52, except the variable is different, right? And that doesn't matter. You can always change what letter you're using for the variable, as long as you're not changing it to some other variable that you're already using, right? So we couldn't like change it to x here, or here we could change it to x because there's no x's involved. But if you already had an x, then you couldn't just change it to x, right? But here we can change t to h all we want, right? What matters is the variable is going to 0, the variable is being plugged into 1 minus cosine, and the variable is being squared. Right, so this becomes the square root of 1/2. Right. Alrighty. So our last problem actually comes from section 2.7, and it's number 36. So let me flip there to make sure I have everything written down properly. So this one is the limits at infinity section. Right, and it was right. And if we use our rules from this section, right, let me make sure I have it down, that as x goes to infinity, x to the n goes to infinity. So if we use that rule, that's kind of like substitution, right? We can't really do substitution with infinity, but these rules count as our substitution thing. That means that we're looking at infinity minus infinity here, right? Which is one of our indeterminate forms. And if we recall from, we had it in a slightly different context when we were doing the evaluating limits algebraically section, but it works the same way. What we really want to do is multiply by the conjugate again, right? So this is going to be the limit as x goes to infinity of square root 9x cubed plus x minus x to the 3/2. I'm going to go ahead and put that over 1 because we're going to have to do a fraction to multiply by the conjugate, because we still have to do it top and bottom because we're still not allowed to change anything. Right. So when we multiply all that out, we square the first term, so we get 9x cubed plus x, and we subtract the second term squared, and on the bottom we get this over again. Alright, so now we get to use our rules for rational functions, where the tricky thing is that we can't really combine these two polynomial pieces the way we really want to. But as we're going to see, and as we can always check for, that doesn't really matter because combining them would just give us the proper coefficient, right? So what we always want to do for something like this is find the leading term of the top and that is for us going to be 8x cubed. All right, let me simplify this so we can see where that comes from. All right, so the leading term of the top is 8x cubed, and the leading term of the bottom, so we don't know what the coefficient is because we can't combine those into one polynomial. But we do know that the leading power is x to the 3/2, right? And even if we had some way to combine those, it's clear they're not going to cancel each other out, right? The square root of 9 x cubed is not going to be canceled out by adding another x to the 3/2, right? So we know that the leading power of the bottom is, right? So this limit is going to go to 8 divided by something that's not 0, right? That's the important thing, not 0. X to the 3 minus 3/2. So that's 8 divided by something that's not equal to 0 times x to the 3/2. And that goes to infinity. Right? So that means that this limit here also goes to infinity. Right? Using our rules for rational functions in Theorem 2 of this section. Right? So even though it didn't start off looking like a rational function, that infinity minus infinity meant that we had to do some playing around with it algebraically, which turned it into a rational function. And so if the leading power on the top and bottom had been the same, then this question mark would have been an issue. We would have needed to figure out something about that. But the fact that the power on top, the leading power on top, is bigger than the leading power on the bottom means that we don't actually care what that coefficient is. It's just going to go off to infinity. Right? Well, we do want it to be positive, but it's going to be like a square root something plus something if we were able to put them together. So we also know it's going to be positive. Right? But the key sort of thing that matters, again, right, even when we have this square root as a piece of something, is what's the leading power, what's the leading exponent on the top and bottom. And sometimes when they're the same, we have to do a little bit more work and figure out what that coefficient would be. But if not, then we can figure out at least whether it goes to infinity or 0. Right? So that's all the problems we have for this week. As usual, let me know if there are any issues, if you want any clarification on anything here. My office hours are in person and virtual. You'll just need to shoot me a quick email and let me know that you want to set up a Zoom call, and we'll get that going. And I'll see y'all next week.